Good morning, afternoon, evening, everyone. This is Ravi Venugopal from OPAL-RT. So I'd like to welcome you all to our webinar on real-time simulation for more electric aircraft. First of all, I'd like to thank all of you for taking time out of your work days, and those of you who are attending after your work day, we're especially thankful for you doing this on a Friday evening. So I'd like to give you a quick introduction of myself. I'm Ravi Venugopal. I'm the Executive Director of U.S. Technical Services. And I have a background in aerospace engineering and working with my talented colleagues at OPAL-RT. I've learned a little bit about power systems and power electronics. I'll be hosting this webinar along with my colleagues Charles Falaha and Alexander Leboeuf. We'd like to apologize. We'd initially intended to have Dr. Luis Herrera from the Rochester Institute of Technology, who's done a lot of interesting work with our systems on more electric aircraft, be one of our hosts, but due to unavoidable circumstances, he's been unable to do so. But we do have Alex Leboeuf, who's substituting instead, and he's got a presentation that covers one of the more important aspects of working on more electric aircraft in terms of integration of systems when you're doing hardware-in-the-loop testing. So again, welcome everyone. And what I'm going to do is give you an overview of the efforts of OPAL-RT in the area of more electric aircraft. Charles is going to take a deeper dive based on one of the active projects, a very interesting one that we have with Bombardier Aerospace. And as I said, Alex is then going to finish up the webinar with a discussion on the integration aspects. So with that, I will kick off the webinar. And I'd like to start out by just, this graphic is something that those of you in the field might have seen before. But really the point here is that electricity on board aircraft has been around for a while, going back almost more than 100 years. And but along the way, it's been growing. And as new power electronic and power system technologies have come online, they've been integrated with aircraft systems. And now, we're up to, on the larger commercial aircraft like the 787 or the 380, we're looking at power levels in the order of 1 megawatt, which really is quite a lot of power. It's like a little village or something like that. But really, we have flying microgrids nowadays. And, with this graphic, I guess I'd like to make 2 points. One is that power electronics technology is really changing things on the way we put in power in the aircraft, and it's allowing us to put in very large levels of power which have to be managed. And this power is being used for a number of purposes, starting from having outlets near every seat to power people's laptops and smartphones and things like that, to actually having larger electrical systems on board for operational efficiency in terms of both, say, fuel consumption, but also maintenance and so on. So, just to go on a little bit on that theme, I'd like to give you a little bit of an overview of the way we're seeing the MEA concept. And essentially, as I mentioned, it takes advantage of various advances in electrical systems, specifically power electronics, to enhance the operational efficiency. And an example could be the utilization of bleedless engines. Right now you use bleed air for the cabin air conditioning or heating systems, and by using a bleedless engine, you improve your engine efficiency. Similarly, by replacing traditional hydraulic and pneumatic systems by electric drives, you gain advantages in terms of maintenance. So all this provides, in addition, a technological springboard for, the idea of an all-electric aircraft. We're a little ways away from that just simply because of battery technology right now or other power source technologies. But, these are all steps along the way. So some of the MEA systems, and this is something that we've had a few years of experience with, that will be coming on board or are already on board on some of the newer aircraft, are listed here. And you have electric environment control systems and anti-icing, and there's a whole list here. But the idea, again, is to be able to replace traditional hydraulic, pneumatic, thermal systems with more electric systems in order to gain operational efficiency aboard the aircraft. So as we're doing this, there are challenges that come up, technology challenges, and one of the first ones is, as I mentioned, we have increased power demand, and now we're talking the order of megawatts, and efficiency really, if you lose a few percent, it means you're losing a lot of energy. And so many of the onboard generation systems have been moving to variable frequency drives, with power electronics instead of conventional geared constant speed drives, which tend to have more losses. But while you're doing this and you're getting more power on board, driving more systems, you want to make sure that your power quality is very good. You want to avoid things like voltage sags and harmonics, because if you have harmonics, you have to add in filters, which add in weight. And of course, being in the aerospace world, reliability is absolutely essential. So while you're validating all this, you have to make sure that your electrical power generation and distribution system is validated across a range of operating conditions that the aircraft will be going through. And as you're putting all this new technology in, of course, it has to go to flight test, but this is expensive, and you want to minimize your risk of failure before you go up in the air. And what we believe is that simulation-based testing can play a very important role in de-risking the introduction of these systems. So here are a few of the things that need to be done. It's not just looking at the electrical system or the power electronics or the power generation and distribution system, but we have to look at the entire aircraft as an integration of systems when we're testing this out, because the performance of the other systems driven by the electrical power system depend on the electrical power system, and it all works together. So we need to test it under a range of conditions, not just your nominal conditions, but also in off-design and fault modes, which are very tricky to do both in the lab and in flight test. And we need to verify that the interaction between and communication between systems are verified. And testing needs to be conducted up to the entire aircraft level. When you're doing this, now simulation of course provides an answer, but the modeling is very complex. There are multi-domain models, multiple timescales. The networks themselves are fairly complicated, lots of breakers, there's redundancy. And then the power electronics works at very high switching frequencies, and to be able to study these, we need to be able to simulate them at sub-microsecond time steps. And to do all this, you have to use a platform with both CPUs and FPGAs, given current computational capabilities. And beyond that, you also need to be able to have very efficient software in terms of numerical methods, in terms of modeling, to be able to run all these complex models at speeds where you can study them, where it doesn't take hours to run a half-second simulation, but eventually also in real time, so that you can go from your model of software-in-the-loop simulation to hardware-in-the-loop simulation. So just to say a little more on that, the idea is that we have to simulate several components. So starting here on the bottom left, you have the electrical network, which would have your power electronics, which need to be simulated on the FPGA because you have very fast dynamics, and then you have the rest of the power system that goes on the CPU. Then you have the other systems, the flight control systems, the actuation systems, the environmental control systems, etc. of the aircraft, which run at slower timescales in the order of, I'd say, hundreds of microseconds to milliseconds running on the CPU. And then you have the entire flight dynamics going on the CPUs too. You have a bunch of controllers on the right that you will also be simulating. And so you have to have a distributed architecture as shown in this picture to be able to simulate the entire system. In this picture, we're looking at doing a complete virtual simulation. There's no real hardware being connected. But if you're able to run all this in real time, you can go to the next step, which is hardware-in-the-loop simulation, where you're still running the plant models on the simulator, but now you have actual controllers connected over on the right through a range of interfaces and IOs to talk to the simulation and carry out your hardware-in-the-loop simulation. And Alex will be talking about this a little later in the webinar. And as I mentioned, now it's just not getting the architecture right, but it's also the solvers. One of the things that you would notice in an EPGDS is that you have a large number of breakers, which means you have a large number of switches. And every time you flip a switch, the topology of the network changes, which means your system matrices change. And if you have n switches, you have 2 to the power of n possibilities for your system matrices. And this means to simulate such a system, you need to hold an enormous number of system equations in your memory. So coming up with intelligent computational methods to be able to handle this complexity is a challenge, and we've been working for a few years now on what we call the state space nodal solver, which addresses this challenge. And in addition, it also enables parallel computing of power systems with short lines, which is a technical challenge in itself. Aircraft have relatively short lines. They're like flying microgrids. And so the SSN is one of those solver technologies that we've developed that is very relevant to MEA simulation. Going on, we also have for the power electronics side of things the EHS solver, which allows you to simulate power electronics, all the switching that goes into power electronics on an FPGA. But the nice thing is you don't need to know very much about programming FPGAs. So one of the challenges that a lot of modeling and system engineers face is that they need to simulate these systems extremely fast on an FPGA, but they're really not FPGA or VHDL programming experts. So with the EHS solver, we have the ability to take a circuit schematic built in your preferred tool like SimPower Systems or Plex or PSIM and have it automatically converted into a numerical simulation model running on the FPGA, which can be synchronized with a slower timescale simulation on the CPU. Finally, as I said, we can now add in the slower systems, the aircraft dynamics and so on, the aerodynamics, and also integrate user interfaces in terms of visualization and pilot input controls to be able to simulate the entire system. So the idea is to build an entire integrated test platform to do this. So this is basically an overview of our approach to studying more electric aircraft. And, at this point in the webinar, we have a little poll question, which we would like to pose to all of you attending, really to get a feel for the challenges that you face when you're doing model-based systems engineering as it pertains to more electric aircraft. So if all of you could take a minute just to go over the poll question. We would appreciate it. So I will now be moving on to introduce our next speakers. We have Charles Falaha, who joined us last year after a very interesting career, starting out as a flight control systems engineer at CAE, the large flight simulator manufacturer. He's worked with Rolls-Royce as a control systems engineer and helped with the integration of Siemens gas turbine division when they acquired that. He has a dual bachelor's in electrical engineering and mechanical engineering and also master's in electrical engineering. And he's leading our effort on this research project with Bombardier Aerospace, where we're working on a technology demonstration project that explores how new, more electric aircraft technologies will be developed, integrated, verified, and validated. And also, as part of that, the idea is to develop a test platform where you can do a lot of this testing virtually, starting with model and software-in-the-loop simulation, and moving on to hardware-in-the-loop simulation. We'll then, as I mentioned, be moving on to the presentation by Alexander Leboeuf, who is our integration technologies team lead, and I will introduce him when he's ready for his presentation. But right now, I will pass it on to Charles. Charles, thank you for taking over.
Thank you, Ravi, for the introduction. So I'm going to give a quick summary about more electric aircraft technology, basically some features and motivations behind more electric aircraft technology. I'm going to also talk about the importance of the technology maturity process that MEA will need to follow, and also talk about the comparison between traditional versus virtual test rigs that Ravi mentioned. I'm going to also finally touch base on the collaborative project that is going on right now between OPAL-RT and several OEMs involving Bombardier as well, and share some preliminary observations, challenges, and some strategies ahead. So the main MEA feature basically is to, as Ravi said, is to reduce hydraulics and pneumatic sources by using more electric loads, such as electrical air conditioning, electrical anti-icing systems, as well as electric braking, for example. And the purpose of it is this will allow us basically to use a bleedless power plant, so bleedless engines, bleedless APUs. And the idea behind that is obviously to have more performance and efficiency on board of the aircraft. So if we take a look between a traditional electric architecture and a more electric architecture comparison, so we see that more electric architecture will provide much more electrical power actually. So in the case of the Boeing 787, which is an example of a more electric aircraft compared to its predecessor, the Boeing 767, we see that it can generate up to 1 megavolt amps, which is roughly 4 times higher than the electric power on board of the Boeing 767. Also, a remote distribution to accommodate an increasingly usage of electric loads. If we take a closer look to the EPGDS, to the electric power generation and distribution system, we can see on a traditional generation system, such as the Boeing 767, we have basically 2 levels of voltage buses, the 115 volt AC and the 28 volt DC bus, with some electric converters such as rectifiers or TRUs. And as opposed to that, on a more electric architecture, here we see much more voltage levels involved and much higher as well. So 230 volt AC bus plus or minus 270 volt DC bus in order to accommodate electric loads that will consume more power. And this is basically to control the losses on the wires on the network. We can also see in a more electric architecture the usage of much more power converters that will feed those electric loads. Another key difference is that in the traditional electric generation system, the electric generators come with integrated drives that will basically control the output frequency on the grid to 400 hertz, whereas on a more electric architecture, we have variable frequency generators, or VFSGs, that are directly coupled to the gearboxes of the aircraft engines, and so they deliver variable frequency to the network that can vary between 380 hertz and up to 800 hertz. Also, these generators can act as motors during start maneuvers in order to start the aircraft engines. So although the more electric architecture is more complex, so why do we go for a more electric aircraft architecture? So we have important drivers to go there basically, and among them we can cite weight, reliability, maintenance, and efficiency. And all four of them really have a direct impact on cost. So for example, for the weight, if we take the traditional IDG generation, we see that the generator comes with a CSD unit that controls, basically it's a mechanical drive that controls the frequency output to 400 Hertz. And this drive weighs a lot more than the generator itself and requires as well its own cooling system. So going to a more electric architecture will involve VFSG that will completely eliminate the need for such a drive, and so weight reduction obviously, but also an increase of reliability. As well, for the traditional setup on an aircraft, the bleeds of the engines and the APU and the start sequence are used to feed conventional loads such as hydraulic components and pneumatic components as well. Going to a more electric strategy will eliminate the use of those bleeds, therefore reducing the losses on the aircraft engine and also reducing the maintenance of such a bulky system by replacing it with an electric system. So we see that there are clear advantages to go to more electric architecture, but this comes with an important aspect to study. Some key points here. Now, since in a more electric architecture we use more power converters, so there is a need to study the thermal losses and also the cooling strategies that will be needed for such equipment. As well, since we have more equipment, more power converters, high switching frequencies, we need to study as well the power quality and the harmonics distortion on the overall network. So that's also an important aspect to look into. Also, in terms of loading, we need to understand, by adding more loads, we need to understand throughout the flight phases of the aircraft the electrical loading on the network, and this will help dimension the wires and the loads themselves. And finally, since we're using more components with more controllers interacting simultaneously on the network, we absolutely need to study the overall stability of the network on both steady state and transient operation. So this brings us to poll question number 2. If you can have a look at it for a few moments before I continue. Right. So we see that there are important study cases we need to do on more electric technology, and this brings us to the fact that a more electric technology, like any new technology introduction in aerospace industry, needs to follow a rigorous maturity process that will bring technology readiness levels, or TRLs, from basic conceptual designs up to flight-proven tests and eventually market introduction. So these TRLs that are widely used in the aerospace industry can also be mapped on a V process, on the traditional V process that you can see on the right. And this process is basically iterative in the sense that if we fail to reach a certain TRL level, we either need to go back to previous TRLs or even back to conceptual designs or functional requirements. And this is shown by the arrows that link the downstroke and the upstroke parts of the V process. Now, another important milestone that needs to be reached is TRL6, which basically features a prototype or a demonstrator in a high fidelity environment, and it's basically a turning point that will allow the development of the actual development of the technology, in our case more electric technology. So typically those demonstrators to reach TRL6 involve test rigs such as the image that you see here in the slide. So this is an example of the test rig that was used for the C-series aircraft, Bombardier premises. And so typically those test rigs involve quite a huge number of equipment, such as pneumatics, hydraulics, electric wiring, which makes the installation fairly complex and also very costly. So the idea here is to basically go to virtual test rigs in order to ensure TRL6, where we would have all the plant models and controllers at the first step in a complete virtual environment. And then the second step would be to take the plant models, such as the models of the engines, the aircraft, electric systems, etc., and execute it on a simulation target, whereas the controller models can be replaced by the actual controllers. This setup is what we refer to as a hardware-in-the-loop environment, and it involves the simulation execution in real time in order to interact properly with the actual controllers. To this setup, we can also add devices such as fault insertion boxes or mapping boxes in order to condition some signals. And the idea really is to have this setup replace the traditional test rig and meet as well the TRL6 level, while minimizing the iterations of within the V process. So as key advantages here, we can cite that we need less hardware and equipment. Therefore, this has a direct impact on cost. It's also a very flexible solution because changes can be made much more easily than on traditional test rigs. Also, we have the capability to do some automated testing, and this is very important in the aerospace field. Plus, it's much more lower maintenance required than on the traditional test rigs. So this brings into context the project that OPAL-RT is actually involved in. So basically, it's a collaborative R&D project that is led by Bombardier Aerospace and involves several other aircraft manufacturers. And the objective of that project is to come up with a virtual rig simulator called MESIS as a TRL6 demonstrator. And the main objectives of MESIS are the study of power quality, control and protection, failure modes and malfunctions, also the interaction of electric systems between them, but with a strong focus on power quality. And the evolution timeline of MESIS, as shown on the right, is basically for MESIS to evolve in a fully integrated hardware-in-the-loop solution by end of 2020. In the integration phase of MESIS, the suppliers will provide models to OPAL-RT that will integrate them on a simulation platform. But also OPAL-RT will provide some models to fill in some modeling gaps, such as electric power converters or electrical machines. And what we look at here is the intended architecture of MESIS. That will involve basically aircraft model and ambient conditions block that will interact with power plant models such as the engines or the auxiliary power units. Also interacting with the electrical power generation distribution system, EPGDS, that will basically create the electrical power and provide it to electrical loads through typical power conversion units such as TRUs, inverters, etc. And then the next phase obviously is to bring that whole set of models into a real-time simulator that is provided by OPAL-RT, and the hardware architecture of such a simulator includes CPU boards and FPGA boards, and those equipment can be those boards can be scaled up to meet complex simulation needs. So within MESIS, we're going to have models that have slow dynamics, for example, and will need to be run and can be run on CPU. And also, we will have, on the other hand, models that will need to run on FPGA, because those models need to go to very small sampling times, because they involve, for example, inverters with high switching frequencies that can reach up to 35 kilohertz. So we see that there are quite some challenges that we'll need to face in terms during the integration phase of the models. One of them is co-simulation. Basically, what co-simulation is, it's basically we're going to get models from suppliers, and those models were developed on different simulation platforms, and we'll have to integrate them. Well, we'll have to integrate all of them on a unique simulation platform, and this requires the development and the propagation of clear integration requirements and documentation to the suppliers. We'll also have to manage all the interfaces between those models, especially for large number of signals. And so the strategy here is to go with an automated generation solution, so that we minimize human error in dealing and creating and managing those interfaces. Also, we talked about models running at different rates. So this also implies the need to manage those models between them, and we need to come up with decoupling techniques to basically separate the models and say, okay, well, models that need to run on FPGA, we need to decouple them and run them at slower time steps, whereas models that need a slower time step, we can put them on CPU. So there are decoupling techniques that we could use. We have strategies for that. Also, it's important to know where those decoupling points will need to enter in order to have the least impact on the grid stability and also preserve accuracy. Finally, we'll have to deal with the model complexity, and if we take the example of the EPGDS, as Ravi mentioned, we will have a large number of contactors that we will need to account for, and basically the increase of that number will increase the computational matrices that will have to be computed. So the idea is here to use the SSN solvers developed by OPAL-RT to improve on that. And this is basically an example of an EPGDS with a matrix structure that we tested, and we were able to reach with those specialized solvers 60 microsecond time step. And just to mention that the loads were also decoupled and run on FPGA with a sample time of 300 nanoseconds. So as a summary, more electric aircraft becomes now a little bit more than a trend, and it becomes a computational reality that aircraft manufacturers need to follow. And so real-time simulation seems to be also an interesting option as opposed to traditional validation strategies, as it is a cost-effective option for more electrical aircraft technology. Also, modeling and validation of electrical requirements and quality and power quality analysis will also be an important aspect to look into. And although we see that there are some challenges ahead, we believe we're going the right way because we have specific tools and know-how that will help us address those challenges. And that's it for me.
Great. Thank you very much, Charles. That was a very interesting review of the various aspects and challenges that we're facing in developing a test rig for more electric aircraft. And in keeping with that, as you mentioned, there are several systems that have to be integrated and tested. And now we'll move on to the second presentation, actually the third, by Alex Leboeuf, who will talk to us about the challenges and the approaches that we use in developing integrated test systems. Alex is trained as an electrical engineer and also has a technical degree in programming. He's been the lead engineer and project manager on several of our aerospace test benches, and many of them involving more electric aircraft and also what's called power hardware in the loop testing for more electric aircraft systems. Alex has a lot of management experience also in terms of, he started out back in his university days as president of his student union, so he's got many talents in terms of running these projects, and he's going to tell us a little bit based on his experience over the years in developing these test rigs. Alex, please go ahead. Thanks.
Thank you, Ravi. Thank you, Charles, also for your presentation. So the content of my part will be basically the hardware in the loop, but we'll also go a little bit more into the details of the electronics and systems integration team, the case studies of which we've been working all along with different customers. The typical project timeline will also be one of the content that we will be addressing today. Automation and visual aids, which will be the most, I would say, new parts into hardware in the loop testing, because those parts were the basics of where the investments were made. But nowadays, it's becoming more and more important to get those readily available for the different test rigs and test systems that will be available. I'll go also a little bit into the benefits and the features of working with OPAL-RT as your integrator for test benches and so on. So a little bit about the team. So the team specifically dedicated to provide turnkey test systems and validation solutions. Originally, the team was created in March 2012 after working on a few test benches for different customers, and we saw a need of creating a specific team that would have as a goal to focus on test benches, hardware in the loop, specific application, as well as the HMIs and the scripting that will be required along the way of the test benches. So also what I may say is that we're currently working on our ISO 9001-2015 certification. So we're upgrading it from the 2008 version that we used to have. So it's a process that is coming. So like Charles mentioned, in the standard V process for validation of a product, Our team specializes in the unit HIL testing, integrated HIL testing, integrated V&V also. But not only that, then you'll see a little bit later that some of our customers actually use our test rig for certification purposes as to diminish the number of hours of in-flight requirements so for certain type of systems, dropping the cost dramatically. So just a little overhead of who's been working with OPAL-RT and in the last few years. So basically Hamilton Sandstrand, CS Communication, Bombardier, Liber, those have been main customers of ours and also partners in our HIL programs here at OPAL-RT. So what is the HIL and the virtual test rig demonstrators that Charles mentioned a little bit earlier, as well as Ravi? So the main purposes are to test the prototype of the controllers and their surrounding equipment, so as to be able to make a rapid control prototyping, for example, where you would test directly a motor, electrical motor, electrical load instead of the controller itself, so as to be able to validate the algorithms that will be required at some point. But not only that, but also the controllers themselves in the hardware environment in which all the IOs are tested. Also, what we may say is that it's used to test the 85% and plus of the lines of codes that have been written in the different controllers for safety measures, and usually and hopefully never used in the life of the aircraft and the controller itself. But it's used to test them in a safe manner, because you don't need to create an engine fire to be able to test it. You could just simulate it on the hardware in the loop and see how the controller reacts, and manage the exceptions that are generated in those cases. Also, the hardware in the loop test benches help us to automate the different test sets that needs to be done during, let's say, for example, a night, a weekend. You can set this up so that way you don't have to have the test engineer at the control of the test bench each minute of the simulation. The automation takes care of the rest. It can be also used as a diagnostic tools whenever there are the prototype of the flights that were made and some errors have occurred and you don't really want to put the pilot's life in jeopardy again, so you can actually go and reset all the configuration to diagnose those problems directly on the ground and rerun those tests over and over again to make sure that everything has been corrected correctly. Like I mentioned a little bit earlier, so accredited certification flight hours can be given also on certain test rigs, with certain validation being done for the certification entities, as to make it super cost effective, as an hour of flight from a prototype aircraft is costing millions, whether the simulator running for an hour would cost the engineers part of the simulator itself. So the cost is really, really low. Also, it gives you the opportunity to validate the interconnected systems simultaneously. By that, what we mean is that the Ironbirds that usually are built for the pneumatic and all the other subsystems can be simulated with different test benches and hardware-in-the-loop environments, in which you can have, let's say, for example, 12 subsystems interconnected all together and validate those all together as being the first validation setup before even taking flight. And the specific part into the more electrical aircraft is the electrical and the power system that we have to add to the HIL setup. So adding up to the purpose that I just given you in the previous slides, we can see that the power validation is used also to test the transients, the hardware redundancies, power capacities, power control algorithm, stability. In a sense that you don't want to see in the prototype aircraft that you power up all the electrical systems at once and it shuts down because there's a transient that has been shot into all the controllers that destroys them or actually put them into safety mode. You can validate it with the power systems directly, either with the hardware in the loop the power hardware in the loop as well can be done. Here I've took the liberty of adding a little bit of our partner and names of partners for the power amplifiers that we've been working with throughout the years. So Puissance Plus, Sametech have been a really great partner, as well as Pittsburgh and Spies. Triphase also, AE Techron, Matsusada, Ponovo and Omicron have been partners with OPAL-RT, and we can use the different specific niche in which each and every manufacturer holds its ground. Also, what OPAL-RT has been working on a little bit in the background is to add a little bit more amplifier power where the gaps are in the different manufacturers that you see here. So OPAL-RT has taken for itself to build also some small amplifier that could be used within those niche. So the little bit of the case studies that we've been working on. So mainly we've been working with APU controllers, air management system controllers, and main engine controllers. I've took the liberty of putting in parentheses the number of systems we've done in each of the main case studies we've been dealing with up to now. And I've put a little bit, I'll put pictures also of the different racks and systems that we've been delivering throughout the years. So you see how much there are some hardware in the loop and hardwares in the different systems with the different FIUs and the different subsystems required for the hardware tests. Now is the time for the third and last pool. So if you may take a while to answer the questions, please. So now a typical project milestones and planning example. So as you can see, most of you have in the aerospace industry have probably already been working with this project and this timeline. Although this one has been a little bit scaled down of the typical project management that we've seen in robust aerospace projects or more heavy projects. In this case, we mainly focus on the kickoff meeting, preliminary design review meeting, and CDR meeting, critical design review, as to make sure that at those meetings, different milestones have a validation timeline for us to work with our customers to make sure that the customer is involved in each and every step for starters, and that all of the specific technical aspects have been covered also at the different steps of the project, so as to make sure that we arrive within a timely fashion at the end of the project with a system that corresponds with the expected results. So on the part of the visualization aids that we've been having throughout our HIL systems, we've been able to add the Explain 10 interface as to make sure that you can see, let's say, how the aircraft behaves with the certain system embedded and the simulations that are at hand with the different errors and everything that you may dish it out. On the right, you can see different control panels that have been designed for the different test benches as well. We use the National Instruments LabVIEW interfaces to be able to do that in conjunction with the RT Lab models that will be running underneath. Visualization again and automation. So in this case, we use MATLAB Simulink. Even though the visualization part is a little bit more or less entertaining, if I may say, it's really robust and offers the main issues and the correct controls, so that way you can have something quick but efficient right at hand. And you can also, in case of RT Lab, do some automation with the MATLAB.m files as to be able to change parameters and also do some data acquisition. Onto the automation, the next level in automation that OPAL-RT has been working on is with Python scripting. Right now, we've in the last year, we've been working, or if I may say, rework our RT Lab Python API by integrating new libraries in it as to ensure that we have new controls over the tests themselves, but not only the tests, but also the configuration. So the previous panels in LabVIEW can be reassigned, the different widgets, and it can be reassigned directly through Python scripting, so as to be able to have different controls available to the technician that does the test, or removed from his direct access, as to make sure that the tests go into a timely fashion and without there being any modification, or directly with the controls that are required for that. What is the test without having the data logger to save all those data? OPAL-RT has been working with the new RT Lab, the data logger. It's not totally finalized up to date now, but I'm happy to say that we've done pretty much around 80% of the new data logger, and have been testing it in our team since the last 6 months, to make sure that we handle the different exceptions and that we have a really good product to offer to the different customers that will be using it in the future. So rapidly going through the benefits and the features of the team, but not only the team, but OPAL-RT. So we control the full business chain. This cannot be said about most of the integrators out there. So we do the direct systems in-house and have a direct influence on the product timelines of the hardware and software designs, with an alignment with the direct customer requirements and the new technologies that those customers require in the hardware and the loop test bench. Also, the overheads are really limited because most of our products are in-house, and we use the off-the-shelf products in alignment with our products in-house as well, and we do design, if required, directly in-house. The support is also directly handled by OPAL-RT's support team and the integration team as well. So it's a heads up over some other integrators that needs to go to the main real-time engine support, which includes delays and limits what you can do with your test bench. And usually you have quick turnovers required in the test environment, which OPAL-RT offers. We have also an open architecture that is giving you access with different subsystems, different software and different interfaces to be integrated in the bench. Modular design, so that way you can upgrade the bench with a really controlled cost approach. Our baseline is built through power electronic simulation as a backbone, so it's a really good propeller for the MEA test bench designs. And we've simplified the project management system so as to keep the development down to, we've been able to design test benches as fast as 6 weeks, whether the typical application usually takes between 12 and 18 weeks. So in the summary, OPAL-RT offers turnkey test solutions that are easily automatable. We propose as much hardware in the loop as Power HIL as well. Some of the tools available are aligned with OPAL-RT solutions and can be easily adaptable to the RT Lab environment. And with this being said, as the aircraft electrification history, if we see in the future that in 2040 the power system will take more and more place into the engineering of the aircraft, I think OPAL-RT will be really readily available and will be also really well placed in helping customers in the future. Thank you very much.
Thanks very much, Alex, for covering the entire integration aspect of MEA HIL. At this point, we'll bring this webinar to a conclusion. I do want to thank every one of you who has attended this webinar. We are most glad to talk to you. If you have any questions, feel free to contact us. And just as I wrap up, I'd like to tell you about a few of our upcoming events. We have our 9th user group conference, RT17, from September 5th to 8th, 2017 in Montreal. We would be very glad if you could attend, and for those of you who are existing customers, if you could present. And also we'll be presenting at the SAE 2017 Aerotech Congress in Fort Worth in Texas. The slides and recording of this presentation will be shared with you, and you will receive an email notifying you of where you can find them. So this is the conclusion of this webinar, and again, thanks very much, and wishing you all a wonderful weekend. Bye-bye. Thanks.